Welcome to Power System Protection Lectures. I am Pratap Mysore. Today I will be covering protection of shunt reactive equipment, shunt reactors and shunt capacitors. In this particular segment, I will cover and just introduce you to the protection of shunt reactors, and then also talk about the different configurations and different types of capacitor banks. And in the subsequent lectures, I will cover the protection of shunt capacitors in detail. If you look at reactive compensation, it allows the system voltage levels to stay within the acceptable limits as specified in C84.1 ANSI standards on the voltage ratings of power systems. And then also it permits the utilization of the transmission circuits for their maximum performance of that you can load them to the desired levels with the use of shunt compensation. So these are the two things which we cover. And then if you, in the next few slides we cover, I am just introducing you to different concepts that are used in the industry. And essentially it gives you an idea what happens when you load the transmission line, or if it beyond a certain limit, or if what happens if it is not loaded at all, how it behaves. So to just introduce you to those concepts, I've provided these slides. A transmission line from a sending end to a receiving end is Vs and Vr is the voltages at sending and receiving end voltage, can be represented as series of sections which has a series inductor and shunt capacitor as shown, and the voltage and current at various points of this line from the sending end to the receiving end is provided by the equations as shown below. In this equation, there's a term beta, that is omega, the angular frequency of the system, multiplied by the square root of L and C of each individual segments of the transmission lines. This is around 2 times 10 power minus 3 radians per mile. And then if you look at this Z0 called the surge impedance of the transmission line, is square root of L by C. These are typically around 450 ohms for a single conductor, and then up to 230 kV. And then it's around 250 to 280 on 345, and then higher voltages. These are typical numbers. Please go back and look at your inductance and capacitance per mile for a transmission line, and then you can calculate these numbers. And charging kVAR is another thing which the capacitance, if you look at it, it is around 1.1 megawatt per mile, or a little higher or lower than that for a 500 kV system, and just less than a megawatt per mile on a 345, and it goes down as the voltage reduces. And the inductive reactance, you can say it is in the range of 0.5 to 0.8 ohms per mile, where 0.8, the higher end, is for single conductor transmission lines, and on bundle conductors the effective inductance goes down around 0.5 to 0.55, depending on number of conductors used. So this is just to give you an idea of typical values. And then if you look at the receiving end voltage in terms of the sending end voltage using those equations, you find that as an example here, if a 500 kV line, which is 300 miles long, if you energize a line with a remote end open, then it could be as high as 130% of the sending end voltage, so which is way outside your specified limits as per C84.1. So if you look at the voltage and current and plot it as shown here, then you get a curve very similar to this. Then and then another one, if you go back and start loading this transmission line, and if you load it with an impedance equal to the surge impedance Z0, this loading is called surge impedance loading, you find that the magnitude of the voltages and currents at various points are the same. So if you look at it, if you go from sending end to receiving end, and receiving end voltage, you have some control to maintain 1 per unit. And then if you have sending end as 1 per unit and receiving end as 1 per unit, then you see if it is loaded to surge impedance loading, the voltage at various points on the line remain the same. If it is loaded less than the surge impedance, then the voltages at various points in between these two sending and receiving end will be higher. And then if it is loaded higher than the surge impedance loading, so the voltages will reduce. So in a system where your loading is not is below the surge impedance loading, the voltage is generally higher than your nominal specified voltage or the voltage at the generating stations. And then if it is heavily loaded system, then the voltages tend to go down. So these are some numbers I have given here. On a 345 425 MVA is a surge impedance loading with a 285 surge impedance, and then a 500 kV it can come up to about 877 ohms. MVA. And now let's look at what happens if you have an inductive load or a capacitive load on an equivalent system, which is represented by an equivalent voltage source with a series source impedance. If I just terminate it with an inductance, the current is inductive, so the current lags the voltage, the specific Vs, by IL by 90 degrees. It's shown here as IL here, and the voltage drop across the source impedance leads this current by 90 degrees. It will be in this direction. So the effective resultant voltage with the reactor with the inductive loading will be VR, which is less than Vs. So now if I switch this with a capacitor, the capacitive current is greater than, is leading sending in voltage, reference voltage, equivalent source voltage by 90 degrees. And then you similarly go through the equations, you find that with when a capacitively loaded system, the VR voltage is higher than Vs voltage. If it is inductive, VR is less than Vs. So this is just an idea of what happens if you have inductive load and what happens if you have capacitive load. Okay, so shunt reactor and shunt capacitors, what do? They try to maintain the voltage within the specified limits during several during different periods of the system loading of the system. So shunt capacitors raise the system voltage and shunt reactors lower the system voltage. So during light load periods, all the transmission lines are connected, and then it acts as a capacitive current, and the system voltages tend to be higher. So under such conditions, you put reactors to pull down the voltage within the specified limits. And similarly, during heavy load conditions, shunt capacitors are used to maintain the voltage. It props up the voltage to be within that specified limits. So shunt reactors are used during heavy load conditions, and shunt reactors are used under light load conditions. So now let's look at shunt reactor, its types and configurations. And then if you look at it, there are two types. One is the dry type, which is an air core reactor, and then the second one is an oil-filled reactor. And then the air core reactors are typically used at lower voltages. So how do you connect a small low voltage reactor to the transmission system? It is through the transformer, and most of the times it is connected to the auxiliary tertiary winding of an auto transformer, which is ungrounded. So that is where these dry type of reactors are connected. Whereas oil immersed reactors are directly connected to the high voltage system, and these are coreless or gapped iron core, and they look like transformers with a single bushing, big bushing and a smaller bushing for grounding on the neutral side. And they are used at both ends of the transmission lines, or they could be used wherever your requirement is needed to reduce the voltage during light load periods. So if you effectively put it in a picture, this is a system at 1 per unit, and you have a transmission line, and then this is the rest of the system where you put the reactor either on directly connected to the transmission system or through a transformer, and by connecting the shunt reactor to the tertiary of the system. You should note that the high voltage system, normally they are all grounded. They are grounded. And then so these connections are always grounded shunt reactors on a direct connected on the reactors connected to the transmission system, whereas these are connected, these are ungrounded when it is connected to the tertiary. So in some installations, because of the inductive switching, the issues associated with reactive switching, breakers are used on the neutral side before you form the neutral. Instead of this here, this breaker will be on this end, and then it forms the neutral on the other side. And then the reactor becomes a part of the transformer protection. So if there is any fault in the reactor, you trip the transformers, associated transformer. Or if it is used like this, you can always just isolate the reactor without tripping the transformers. These are two different arrangements that are used, and physically they are always generally assumed to be put as as the terminals or vertices of the equilateral triangle. The intent of this is that effective induction on any fence or a nearby metallic object is reduced because they are equally spaced. Oil immersed reactors, you can either use a breaker to connect it to the system if it is bus connected, or if it is a line connected, and then or it can be directly connected to the system. And sometimes they are directly solidly grounded, directly connected to the ground, or it can be connected to a neutral reactor. There are applications in single phase tripping and reclosing. When you trip only the faulted phase, the arc continues to flow because of the capacitance from the other two phases. This is called the secondary arc. Even after the breaker opens, to quench this arc, we use neutral reactors, which compensates for the capacitive coupling. Reactor failure modes, insulation at phase terminals is extremely common, is the most common type of failure modes of the air core reactors, and there are turn-to-turn, that is most common type of failures. I forgot to mention that air core reactors are now available at 345 kV also. They are stacked small low voltage reactors and then insulated up to the high voltage. This is development in last few years. Earlier we were using only the oil-filled reactors at transmission levels, but it is now available up to 345. Then coming back to this, insulation failure is always at the phase terminals, resulting in turn-to-turn faults. That is the most common type. And then it starts tracking, and due to contamination, it will it deteriorates, and then the failures occur. Overheating due to high circulating current in the shorted section, that results in a complete flashover of that particular winding, which puts phase-to-phase voltage on the unfaulted phases, and that results in thermal damage. When you look at when you look at the configuration, phase-to-phase faults are not very common here because they are physically put as three vertices of an equilateral triangle. They're physically separated. It's very rare that it happens, and also it is an ungrounded system, so phase-to-ground fault is also arcing. If there is a phase-to-ground arcing, then the arc current is also very low. There are reported incidents of arcing single-phase faults evolving into phase-to-phase faults, and that will create a two-phase to ground, and it will have a short-circuit current. So one of the common methods, oil immersed reactors, you can look faults resulting from high currents. When does it high current come? When you energize a oil-filled reactor, it is less like a magnetizing current. But the difference between a transformer and the reactor is switched in and switched out more often than a transformer. So that results in higher in these reactors seeing high magnetizing currents, which also creates failures. There are methods now. They use controlled closing and controlled opening on oil immersed reactors to prevent failures. And then on air core reactors, we just use controlled opening to prevent any reignition. This is beyond the scope of this, but just I wanted to mention it to tell you that there are issues of switching any inductive loads, especially the reactors, both at the low voltage level and at high voltage level. Coming back to this failures, there's a small change in phase-to-phase current. If there is a turn-to-turn fault, you cannot detect from phase-to-phase, and that causes failures. And then if because it is a magnetic core, higher voltages produces overfluxing in this, and then it causes failures. These are used to pull down the voltage, but the compensation, the magnitude or the megavar may not be sufficient to pull down the voltage within the specified limits. So the reactor itself is subjected to over voltages in a transmission system. Then you need to have the protection to disconnect it and trip the line if the voltages are much higher. On the air core reactors, which are used on the tertiary of the transformer, this is a voltage differential relay. We look at the zero sequence voltage on the bus, distribution bus here. It could be 13.8 up to 34.5 with the neutral voltage here, which is monitored with another PT here. Or a resistor potential device, which is most cost effective that is used in these applications. And this resistance is used for just damping out the oscillations because of the bus capacitance and then the system inductance. And that is why it is used, but it is out of the scope. I just wanted to mention it here. So if you look at it, for an external fault, the measured V0 will be same as Vn, and then but for an internal fault, these two are not equal, and that is how we detect if there is a fault internal to the reactor. This is a very common method that is used. And then the other one is overcurrent relay. You can set it so that if the current exceeds its nominal rating, then you can trip on a time overcurrent, or if it is set to about 2 to 3 times. For instantaneous. And phase to negative sequence also is used, but negative sequence you have to be careful that it has to be coordinated with the relays in the transmission systems. For external faults, it should not operate. So these are typical overcurrent protection that is used on the shunt reactor, air core reactor, and the voltage differential is very common on an ungrounded reactor system. When you look at the oil reactor, it is same as a transformer. So we use a transformer differential relay with CTs on the phase side and the neutral side. And then you can also use 3 phase CTs and 1 neutral CT and form 87N function, which we covered in transformer differential protection. In addition to electrical sensing relays, because this is similar to construction of a transformer, we use gas and oil pressure relays similar to transformer protection to detect any overheating or to turn failures inside the transformers. Over voltage relays also, these called over voltage relays are used to take the reactor out of service if the voltage exceeds, and then if there is overfluxing in the cores, or you can use volts per hertz also on this to prevent failures due to heating of the core at higher voltages of the system. So shunt reactors can be directly connected to the transmission line. In addition to using this, if there is any severe fault, the transmission line distance relays also will trip for faults inside the reactors for higher severe faults. We always use a reactor protection to detect where the fault is, whether it is a transformer fault or a reactor fault, and then high current faults are detected by the distance relays. The issue, but using the distance relays to on directly connected shunt reactors is the zero sequence reactance changes due to the addition of the impedance. So your distance relay settings has to be accommodated, corrected based on the change in the zero sequence due to the addition of the shunt reactors on the transmission line. Shunt reactors are very highly inductive, so X over R is very high. So whenever you energize that, you get very high DC offsets, which might result in saturation of the CTs and misoperations of the distance relays when you are energizing. And similarly, when you have when you de-energize a line with a shunt reactor, the trapped charges on the line and discharges, and then they oscillate with this shunt inductance and produces voltage and current oscillations if you are using current from the shunt reactor into the distance relay. And this might cause a misoperation of the relay. Even when the breaker is open, the distance relay may operate and show that there is a fault. So these are some things which you should be aware of. And negative sequence operations also due to CT saturation have occurred when energizing and de-energizing this reactor. So yeah, most of the times these need to be either taken out of service when you are energizing and de-energizing, or there should be adequate time delay to prevent misoperation of the negative sequence elements due to severe CT saturations. The great standard, IEEE standard that discusses in detail is C37109. And then you can also look at transformer protection guide. And the reactor can be taken as a single winding transformer, and they can use the same protection methods that is discussed there. Now let us switch our gear to shunt capacitors. As I mentioned, that is used to prop up the voltage during heavy load conditions, and then the local voltage supports or the banks, that is this, we switch in the banks when the voltage is lower than the specified limits, and then it could be a local voltage supports. If there is an inductive load at a customer, we can put capacitors at the customer side to prop up the voltage when they, for example, energize a large motor, or when there is a high inductive load that is switched in, to prevent voltages from collapsing to very low values, which we discussed what happens when you have an inductive load connected to the system. So these are switched in at 15 to 20 seconds, or they are switched in whenever you switch in a large inductive load. And then the size of the bank is always taken as about 3 per. You don't want the voltage excursion to be more than 3%. And then this is to prevent, in a transmission system, you size the capacitor banks so that your change in voltage is not greater than 3%. This has come from the historical curve, GE flicker curve of the 1950s, where they conducted an experiment to see what causes irritation to people. And that is how, and even now, this is used in the industry as a criteria for sizing the capacitor banks. And then system voltage support, when there is a power flow through the system, we said that when a transmission line is loaded more than the surge impedance loading, the voltages at various points drop down. So to prop up the voltage at these points due to flow, it's not for the local voltage support, it is for the through flow of the power through the system. We need voltages, we need capacitors at various points to keep the voltages within the specified limit. And they are also used for fast switching when there is an impending voltage collapse. Suddenly the voltages keep on going down and they might fall. So you need to prop up the voltage by putting the capacitors to prevent any voltage collapse. Or for stability reasons, we sometimes put in extra capacitors, which are switched in about 5 or 6 cycles, much higher than the SVCs, which come in very fast, well within 1 or 2 cycles. Let's look at the capacitor unit construction. They have a discharge resistor here, and then they have series of elements, in series and parallel. This is a very typical construction and filled with insulating fluid. And then the voltage range is from 2.4 kV to 24.9 as per the standards and IEEE 18. And then they go up to 800 kVAR. And the terminology they use is they don't use a capacitor can, they call it a unit. And then they could be either single bushing with only one bushing with this terminal connected to the case, or they could be insulated and then they can be brought out through the insulation. So discharge resistor is used here, and they have elements here and then they are configured in series parallel combinations to provide the required to get the required voltage and required kbar. So when you look at the discharge resistor, it essentially discharges when you disconnect a capacitor. There are trap charges, so you want to make sure that it is less than 50 volts DC in 5 minutes. So the discharge resistor is rated accordingly by the manufacturers. And then if you look at a capacitor element, it is just aluminum foils with insulation between the two aluminum foils. And this is plastic film is used. Older units used craft paper. I think this is extinct now. And then they are not up to 2 kV. They are typically around 2 kV. It could be higher than that a little bit. These are the typical ranges, and that is how they are designed. And the design can change, and they can exceed this. But this is the present design standards. They design by the standards used by the manufacturers. So what happens because of the voltage stress? It punctures between the two electrodes, and then it shorts the two aluminum foils, the two electrodes, resulting in a short circuit. So when it shorts here, it essentially takes away one full series element out of this. So if you have a voltage which was divided equally between all these elements, if one element is shorted, the voltage across the remaining elements increase and produces more stress. So the failure mode is always puncturing of the insulation and shorting of an element. So if the voltage increases, the standard specifies that it should be able to withstand 110% of its rating continuously. And then as the voltage increases, the allowed time reduces, and at 220% of the rated voltage, you have to take it out of service within 6 cycles. That is the withstanding capability of this. But something you need to mention when you design a capacitor bank, you have to make sure that it is rated at the nominal or maximum operating voltage, whatever you desire. And you should not be using this 110% for designing a capacitor bank that under normal conditions, it is always operating above its 100% rating. IEEE 18 provided an addendum which very clearly said that these capacitor banks should not be rated so that it is operating continuously above 100% of its rated value. There are different types of capacitors. One is called externally fused, second is fuseless, and third is internally fused. Bank connections, you could be delta or a grounded Y or an ungrounded Y. These are very commonly used configurations. And you also have an edge-connected, bridge-connected windings, which I didn't mention. These are typically used in internally fused banks. Externally fused was very common in North America. This is changing at higher voltages because of economic considerations. These are getting replaced by fuseless banks. Here, the capacitor units are individually fused with expulsion or current limiting fuses, and fuses are replaceable and are mounted external to the capacitor unit. I will show you a picture of this. Here, if you look at it, these are all the fuses, and these are single bushing capacitor banks. And then they have a lot of capacitors in parallel here, with each one connected by a fuse. And if there is a problem with this, all the energy of the remaining capacitors discharge into this, blowing the fuse, and then it gets isolated. It gets disconnected. And then if you walk around, you can see that this tail has dropped off. So then you know that there is a failure of the fuse. If you look at the next picture, you see this is how it is connected. And what we do is we monitor the voltage across the last series group here. It is just an arrangement of series parallel capacitors units with the fuses. And here in this example, I have got 3 series units and several parallel capacitors in each string. And then you have a transformer here to monitor the voltage here. This will be used in our differential schemes. Yeah, it's same thing. Capacitor bank is made up of groups of parallel units connected in series. Failure of an element causes an overvoltage on the remaining units, and there is a cascade failure within this, and other capacitor units are connected in parallel, and failed units are force the fuse operation. If we covered it, these are all single bushing and internally fused. Each element is fused inside, and these are used outside United States very commonly, and then it is also used in a lot of applications in series capacitors and static war compensators within United States. And then I don't have a picture of this, so I have given a fuseless bank. These are connected without fuseless in series strings, and the idea here is to limit the volt current through each one of these to less than 75 amperes, so that you don't have, if the element shorts, you don't have too much energy to open circuit that. And we will cover this in the next section. I'm just showing you these. And then typically externally fused was a single bushing. Fuseless and internally fused are always with two bushings, double bushings. Fuseless arrangement are correct in series and between phase terminals and neutral, but there are no parallel connections in between. And internal elements fail, and we limit the current to 50 to 75 amps. As I mentioned, it is to prevent overheating and then opening of the short circuit. Sensitive unbalanced detection relaying removes the bank from service when sufficient elements have failed. Again, what is the criteria here? If it exceeds 110% of its nominal rating across any element, then we